think we know what to do with it. Okay, so we're very pleased to have Qiyang Han, who's an associate professor at Rutgers in the Department of Statistics. He is an alum, so he graduated in 2018 under John Wellner. Let me tell a little bit about his research. His research lies at the theoretical inference of statistics, algorithms, and probability. He's one of those people who does very deep and high quality work. Not many papers, but each of his papers is truly outstanding. I had a pleasure of reading some of his recent papers that focuses on connecting first order optimization methods with inference, iterates of these first order optimization methods with inference. He had a really beautiful recent paper in Annals of Statistics that I highly recommend. I think it was called Gradient Descent Inference and Empirical Risk Minimization. So I think he'll talk a little bit about that line of work. So please welcome Qiyang.
So thanks very much for the very kind introduction, and it's a great honor and pleasure to be back here. So everything seems very similar at the university, and of course I'm looking very forward to meeting with all new people and new friends. So today I want to talk about some recent work, as Armin kind of introduced. It's kind of a serious work on the topic of algorithmic inference by nonconvex gradient descent. So this talk is based on joint work with this now. Yeah, it just kind of gets stuck. Anyway, okay, so this joint work with fantastic collaborators, Masaaki Imaimi from University of Tokyo, and Xiaofeng Xu, who is now doing postdoc at USC. So now, before diving into a bit more details of what I will talk about today, so let me just give you a kind of a textbook recap of what we actually know about a very long line of classical statistical inference paradigm. So in this kind of textbook inference paradigm, what we have is we first collect the data, and then we build up a kind of a simple and interpretable model for which we want to test in some parameters. And then for this kind of interest, we typically design some integral risk minimization procedure for which we try to minimize a loss criteria and then estimate this parameter. So with this parameter being estimated, we have lots of known methods that can help us to do the inference and quantify its uncertainty for the statistical purposes. So to give you a bit more concrete example of this kind of method, which is kind of one very detailed, but it's not exhaustive at all. So suppose we have this data collected in this abstract form. Remember, we have a data matrix X and a response variable with in the regression set. And then we build up a linear regression model where we postulate that the response has a linear relation with your basically correlate, and then we're interested mostly about this regression coefficient or regression vector that's for the new stuff. Okay, this is how we build up a simple model. And then we have a bunch of statistical extension procedures for these purposes. For example, we can take the classical one, all about lasso. We take the square function and then do a regularization, and then it's going to give me the estimate. And we compute it very nicely. So why is this guy going to be very easy to compute? Is because we know that the objective is convex, and then what we did is we can just run kind of algorithms, and we start not. We don't have to design very specifically how the algorithm is to do. We start somewhere, and then algorithm is going, when we run algorithm, some gradient descent or crossing gradient descent is going to basically converge quite quickly to the global optimum and give me a solution. Okay, and then with this solution, the lasso itself, you probably cannot do directly with the inference part, but we find out a lot of techniques that tells us how we can actually convert something which is not committed useful for inference into the inference purpose by deriving stuff. Okay, and then we get something that we get normal statistics for which it has normality, and then we can do inference based on this kind of very useful. Just give you one example of this kind of a classical inference part. Of course, as I said, this is not going to be exhaustive, and we have very different and vast pool of techniques of doing this kind of analysis. So what is the trouble of this kind of classical paradigm in the modern sense? The first trouble, of course, is nowadays in this more modern learning techniques, we don't actually use linear models. As an example, already in the very simple set, this is kind of a just a multilinear neural network. This is an extremely non-linear function, and actually by today we still don't know many of the mysteries of this kind of learning learning dynamics of these neural networks. But one of the key takeaway here is that traditionally we take a kind of very simple model, for example, linear model, to consider. But now we're not actually doing this. So we can build an extremely complete model, and this multilinear is just one of the simplest of such. So what is the consequence of using a very complicated model? So one of the consequences is that now we don't have a very tractable integer risk minimization from optimization perspective. And why is that? So for example, typically, now we deal with enormously complicated statistical model, and then the algorithm we are going to try to do is not that complicated. Conceptually, it's just doing kind of the first order gradient descent methods with the stochastic descent, and because there are lots of tweaks and engineering, for example, we have different types of step size, scheduler, so on and so forth. But in concept, we still kind of doing simple algorithm for this kind of thing. But simple algorithm is not going to give you simple answers. And the reason is also very simple, because the model is extremely complicated. We're looking at the loss landscape of this algorithm, and it's going to be extremely complicated. We don't have that much structure. The loss landscape can be, this picture is not very clear on this kind of a big background, but the point here is that you may have extremely lots of local outcome for which you don't actually know where something is going to converge. Although the empirical performance is extremely good, but theoretically you actually don't know where the algorithm is going to perform in a rigorous sense. Okay, so you may start the algorithm at somewhere, and then it may start at the local optimum, and you actually don't know where the optimum is. So this is typically what you should expect in this nowadays learning. Okay, so now in face of these challenges, we no longer have a simple model. We're working with an extremely complicated model architecture. And so one of the consequences is that we don't have a tractable integer risk minimization. So in parts, we're going to use such a simple method like the gradient descent, but theoretically, actually, it's more or less beyond the reach of human understanding of how it actually behaves. So now the challenge here is that we've been trying to do these kind of classical steps of inference and developing all these methods for so many years. And are all these methods kind of still relevant in this kind of extremely complicated model learning settings? Should we just get rid of these kind of ideas and then simply trying to do something? We have different techniques, algorithms, and treating algorithms as black box and so on and so forth. But are these kind of classical ideas should just be post-studied and forgotten? So in this talk, I'm going to try to reconnect some of these classical ideas to a bit more modern settings, perhaps in a bit more non-standard way. And one of the takeaway that I want to show here is actually still these classical ideas would actually be very powerful if you think about this kind of concept more deepness. Okay, so this is kind of the overall bigger picture I want to talk about today. So let me start with a simple model, just trying to illustrate some of the essential difficulties within this problem. Okay, so I'm not going to start with very complicated. So I'm just going to start with a simple model which we can think about the problem from a bit more fundamental perspective. So when we start with what we so-called a single index model, which is also known as a one-layer neural network. So in this model, what we have, we observe data, which is in the form of a response y and a feature vector an. Okay, so it's going to live in a dimension n. And then we put a model, which is the response is a potential nonlinear function transformation of a linear projection of the covariate and its sequence. So what is different from the linear model is just we have a potentially nonlinear transformation over here, but that's going to complicate things part of it, as we'll see very soon. So this model is known as the kind of the toy model, but also it's very interesting because this is going to be this kind of a one-layer neural network model, and we'll see very soon it's going to capture some of the essential difficulties in this approach. So just for notation, let me denote m as a sample size and n as a signal dimension. So this is going to be slightly different from the classical statistical dimension, but it's going to be useful for our purposes because it's going to connect very naturally to the notation people use in information theory using probability. Okay, so I'm going to use this notation. So for our statistical purpose, our target is going to be interested in this unknown signal new stuff. Okay, can you see here? Why not? Okay, so now let's continue with the classical idea and try to use the integer risk minimization procedure. So we observe data a and y, and now let's take a loss function. Okay, let's take a loss function and take a regularizer to promote whatever structure we want to promote on signal. For example, if we choose L1 regularizer, then we want to promote the sparsely, it doesn't matter, but we can choose an abstract regularizer. Another idea for this integer risk minimization is we want to looking for an estimate that's trying to minimizing the objective. Okay, and then in practice, how do we actually compute that? We want to use this one as an estimate for a signal, and ideally, if possible, we want to use this estimate for inference purposes later. But now, the first thing is that this one, if looking at this, seems to be something quite simple. But now, in order to compute it, for example, by this first order methods by gradient descent of proximal verb. So if you don't like proximal, you can forget about that. So the proximal verb is just for this regular number. So if you have regular, you use the proximal verb. If you don't have the regular, you just forget about this proximal things. Just run gradient descent. So now let's try to run this gradient descent algorithm for this objective. If the objective is, for example, very nice, you have very nice strongly convex property, then this algorithm is going to converge to linear, extremely fast. This kind of class knowledge optimized. And also, if you only have the convexity, this algorithm can also probably be very efficient in many cases. But now, in our kind of toy model, there's already a difficulty. This is very simple. We already see the difficulties in this algorithm. So why it's going to be difficult? It's because typically the loss density in this setting is already highly non-convex. So let me give you a concrete example. Example, we can think about we have a sigmoid link function, which is we take the link function to be the sigmoid function, which is a non-convex function, and this function looks like this. Well, this is not unnatural at all. It's just kind of one very commonly chosen function in neural network. And now we also choose a very natural loss function, the square loss function. Okay, so everything is very natural choice by this point. And then we're looking at what is the loss landscape. So this is probably not very visualized in this grayscale, but now let's look at this is going to be the contour of the loss function. So this is a very typical scenario we'll see in non-convex optimization. So this is a very local region. So in this local region, you'll see actually there will be two local optima. And if you start the algorithm somewhere, okay, start algorithm somewhere, and you can see it's not guaranteed to converge to even the better in two of these local optima. This is going to converge towards this local here. And then you're looking at this loss landscape, and then see actually the outcome is not going to converge something you might actually want to converge in this even in this local region. Okay. So what is the trouble? So because of the loss landscape is typically extremely non-convex, our iterate may not converge. And even the iterate converge, the converging point may not be the point you are interested, so it may not be able to do the inference service as desired. So now with all these kinds of challenges, of course, there's a very long line of work trying to, for example, just directly tackle how the optimal dynamics look like and trying to understand what happens for this converging point and trying to figure out by model specific and so on and so forth. But in this talk, I'm going to take a different perspective. So the perspective I'm going to take is now, given that we know the algorithm typically we may not be able to successfully converge because the learning dynamics is extremely complicated. And even if converge, we may not be able to use it for inference. So the perspective we're going to take is, can we just use the iterate itself as a statistical estimate for the purpose of inference? So this is going to be the key perspective we're going to take in this study. So I'm going to show you that actually this is possible. For example, we're going to work out in the example of gradient descent. So this is going to be possible by just augment the gradient descent by a few auxiliary computations. I'm going to show you that our proposal is going to lead to a valid framework for inference of the signal in the so-called photology. I'm going to explain later on. But the main feature is that the inference is going to be valid at each iteration. And it's going to hold on the very general non-convex loss landscape, and it does not require algorithmic dependence. Okay, so this is the feature of our new proposal. So now, before I talk about how we can actually do this, let me take a detour to some classical knowledge. So this is the knowledge we actually know for more or less more than a decade about the Debye's law. So let me just kind of give a recap of this concept in case you don't know these kinds of things. Right? So we know that Lasso is you solve the convex optimization problem that was sliced, and then if we want to use Lasso for inference, we have to do a bit Debye's law. So how can we actually implement this this program? So for Lasso, for example, we know it's going to be more or less like a three-step procedure. So the first step procedure is we're looking at what is the distribution theory for Lasso. And now this is something wrong. So let me just for simplicity, let's assume that you have the isotrope design on feature vector. And then we know that Lasso estimate the distribution is roughly something a proximal operator applied to R1 applies to a Gaussian sequence model where the signal, we have a central signal with a Gaussian. So what you have for, so what you think about this Lasso estimate? So roughly speaking, the distribution is just you apply this proximal operator for R1 is a self-specially operator. Okay, you can think about it's going to be a nonlinear function. So how is it applied? So you have a sequence model, you have a signal provided by Gaussian noise, and then you're going to apply a self-specially operator on these times. So this will be the distribution of the Lasso. Okay. So of course now you see why the debiasing is necessary is because the Lasso you don't have like an asymptotic by itself. So the Gaussian noise is hidden in a nonlinear transformation. So the key idea of doing the debiasing Lasso is now we're trying to deactivate the effect of this nonlinear transformation and trying to get out this Gaussian component. So what is the proposal we know in literature? We know that this will be possible if we start with the Lasso estimate, which has this distribution. It's going to be a nonlinear transformation applied to a Gaussian vector with mean given by a signal. So the correction we're going to do is we're going to do a correction as direction of its loss derivative. Okay, so for Lasso estimate, we have a square loss, and then we just take the derivative of the square loss, and then we're going to do this correction around this loss derivative with certain correction factor. So the correction factor has to be chosen in a carefully. And actually, it has a closed form. This is a closed form. This is a theoretical version or value of this factor for which we have to choose. And then the point here is that we start with Lasso estimate, and then we correct it in the direction of this loss derivative with certain choice of the weights, and then it will retrieve asymptotic map in the sense that we basically deactivate this nonlinear function and then expose our device Lasso with centered at the signal and a Gaussian noise. Okay, and now we construct the statistics using this kind of a one-step correction. And then we get back to the asymptotic normality. And then once we get the asymptotic normality, the remaining thing is we want a data-driven way to estimate this debiasing coefficient. And then once we can estimate this debiasing coefficient, we can convert everything into a data-driven way to estimate what the next statistical inference will approximately see. Okay, and actually this part is easy because we can looking at this closing formula, and then there's a very nice correspondence to the equation. We just going to use the sparsity of the Lasso to do this adjustment, and then that's it. So this is what happens to Lasso. So Lasso is a convex, it solves a convex objective. So it seems has nothing to do with what we want to do, because we want to do things extremely non-convex. But actually we're going to take the inspirations from this three-step construction, and we're going to show you that we can propose a debiased gradient iterate, essentially following the scheme of these three steps conceptually. Okay, so now in the first step, we're trying to looking at the distribution of the gradient descent, very precisely how we can actually do this. So it proves that this is for simplicity. We assume that this this design matrix has IDs of Gaussian entries and mean zero and variance. And then what we do is we have a distribution theory precisely characterize how the gradient descent actually behaves. So for example, we can look at the second display here. Okay, this is basically give you a distribution characterization for this gradient descent. So you're looking at what happens as the iteration t. In distribution, it's going to roughly the same thing as an the proximal operator applies to a linear combination of all past iterate with a signal component and a Gaussian noise appearing as the t situation. This is the structure of what we actually uncover from this gradient descent. Okay, so you can see actually there's a structure similar to a Lasso case. So in Lasso case, you don't have this kind of law because it's not an iterate, it's just an estimate. So in Lasso case, you just have a proximal operator applied to a signal plus Gaussian noise. But now for this gradient descent iterate, because it's going to depend on this past iteration quite non-trivially, and we can actually characterize this distribution in a very precise way, in the sense of looking at the distribution is going to be exactly given by something conceptually similar to Lasso. But now the correction has to be done with a linear combination of the past iterate. So the coefficient here will be very important, but I haven't told how this thing determined. I just tell the existence of these coefficients. So these coefficients are for this such corrections. I'm not going to give the formal definition, but essentially, these kind of numerical values can be determined in a recursive way. I'm going to talk about this from the later. So at this point, it's simple. There exists this kind of numerical value for which we can actually have this representation. Okay, this is for any questions.
Can I ask so this is like a single index model, but what made it, so I see that you've got the psi star and then you've got the self-differential sitting on the outside, but in principle, this is not more general than just a single index model? Like what particularly did you use about the single index model?
So I think the single index model part is actually determining these kind of coefficients we have to.
Oh, I see. So it's about actually computing those coefficients.
Yes.
And I guess it becomes harder and harder as you generalize.
Exactly. Other questions?
But otherwise, this is a general theorem that says like there exists these coefficients for a more complex model. Like it will always look
Yeah,
like
but then
this, but just
I wouldn't say it's always look like this, but I think you can think of if you have a model for which you can have like a physical sense, like the outer closure of the single index, and it's not assuming it's from that and it's assuming obviously the bigger thing from like this. But this is only going to give you a very general class of functions, because in a Gaussian space you can just do the expansion on the chemical number and this kind of now it's going to cover the kind of sentences. So I think it's going to be very. Yes. This is a very good question. I'm going to come back to this later. So this is actually holds in a sense. So this holds in rigorous mathematics. This is going to hold in a sense when the problem size goes to infinity. So this is going to hold for each iteration, and the current iteration, the current bound we have is this is going to hold for each iteration. If you send n goes to infinity, which means that the system size is very large, and then you get this kind of approximation, or you get this kind of distribution approximation. So what I would believe is that if the problem has kind of so the key point here is that all these kind of things goes without any convergence guarantee of the algorithm. But if the algorithm is going to converge very nicely, and I believe this will actually, as this is still conjecture, you should be able to refine the bounds to take into that, but this is still open. So as I mentioned, one of the key features here is that these kind of results, it does not actually require any convexity on this online objectives, subject to some smoothness. So this is not like you put this set of conditions on the Gaussian has to be convex and so forth, and you do these results. And then we can categorize the distribution of the iterators in each iteration. Okay, and we can also do this similarly for this data matrix applied to this iterate, and I'll get a different representation, but I'm not going to talk this a bit too much. So this is the first step. I love to do association. We try to nail down what is the distribution for these gradient and iterate. And then the second step is now, because this distribution, if you look at that, it could be extremely complicated, right? So conceptually what you're doing, so you can start from iteration 0, get some signal plus Gaussian function, and you're going to convert it with a nonlinear function. And then you do iteration 1, you get another nonlinear function applies to already the first iteration plus another signal and Gaussian. So you're going to do this for many iterations. So after a few iterations, this becomes extremely complicated. You can actually know how this actually behaves in an analytic factor way. So the question now is, can we actually mimic the idea of device factor and trying to expose these Gaussians out of there and actually get over there? And actually conceptually also very similar to the device factor case. So this I'm going to show you. So the proposal is now we have the current iterate. I'm going to do a devising by a suitable linear combinations of the loss derivative values at all past iterations. So if you still remember in the last case, I'm going to do this comparison later as well. In the last case, what we have is we start from the estimate. You can think about this is going to be the endpoint of the algorithm, and then we do a one-step correction towards basically towards the loss derivative. But now for this iterative algorithm without complexity, what we do is now we start at the current iteration. We're going to do a device with a linear combination of these loss derivatives at all past iterations. Okay, and then this devising coefficient is going to determine in very specific way. We have to design this devising coefficient in a very specific way. So it's going to be given by the inverse of this matrix tau, and this matrix tau is actually the result. this matrix tau is actually carrying this linear combination over here. Okay, so at this point, I haven't told you exactly how this formula, but we're going to get to that point. So now we know there's actually a way to debias in the consent and expose the Gaussian component all the way. And with this step, you can prove that this one, the debias gradient H rate, is going to be approximately normal distributed with a center is going to be a scale version of the signal and a bottom. Something like this. So this is also in similar conceptually similarity to the debias start of this. So the last step is also very similar. Is now at this point we have this debiasing coefficient. It's determined theoretically. Okay, so actually we know the existence of this coefficient, but we don't actually know how to construct data-driven versions. So in the last case, things are very simple. So if I go back to last case, what we do is we just basically have a kind of one-line formula for them, which is very simple in last case. But now for this iterative algorithm, yes.
No, that's right. Just finish.
But for this iterative algorithm, actually one of the difficulties we don't have a closed iterative formula for this kind of
So if I just look at mu t, obviously because it's non-convex, there is like no hope that we'll be necessarily anywhere close to mu star, even if we let t go to infinity. But I guess the amazing thing here is that the debiasing allows you to actually get something about the truth.
Exactly.
It's very non-convex.
So this is actually we start with iterate. Maybe from you can think about it. If you start with a random base, so you may or may not have lots of information about your signal. And now as the iteration goes, you may have some partial information about your signal, and that's going to be captured in this coefficient. And if you think about it in last case, it's going to be one. Yeah. So in a sense that if we do that, so basically the convex objective and going to close to exact signal. In a sense, in some way you're going to be close to that with trivial signal. But in this algorithm, you're exactly correct. It's not convex. You may not be very close to the signal, but still there's some partial information you can get them.
So depending on the initialization, this B thing, for example, could be very far away from one.
Yeah. And actually, depending on the problem, for example, in the phase retrieval, these kind of things can be just like one of the first. Any questions at this point? Okay, so now at this point we have kind of an abstract formula for this debias coefficient with a theoretical debiasing coefficient, which we actually don't know yet how to compute it. So the key question at this point is how we can actually compute this coefficient.
Right, so just one other question. The debiasing is related to the regularization, I suppose, if you have in the subjective.
Yeah.
Right? But if I didn't have the regularization, wouldn't you put debiasing step and you would still have the similar results where this would be is.
So without since every single point, there's one good thing about without using regularization is that if you don't have regularization, then the iterate is going to be Gaussian distributed by itself for each iteration. But there's a caveat in the sense that you can take very easy example for which you can have iterations. For example, at iteration 2, iteration 4, iteration 6, you get the mean of the mean. So in a sense, we don't do B-bounds, then you may not be able to retrieve the information for them. Okay, so now I'm going to talk about the third step. The third step is exactly how basically the analog from last is how we construct the dividing coefficients. And here there's actually a completely different proposal. So the key difficulty is I'm going to talk about this kind of later on is that this kind of matrices tau is going to be determined in a recursive way, and typically it's not going to be analytically tractable. So you cannot write down the precise formula, but you can write down the recursion, but cannot write down the precise formula. But still, we can estimate these coefficients in a data-driven way, in a sense that we can actually provide the estimate for these matrices iteration by iteration. So suppose now, for example, everything is estimated at iteration t-1. We have this kind of algorithm that helps you to construct these kind of estimates at iteration t. Okay, for example, suppose we have already this estimate at t-1, and we want to compute the estimate of tau at iteration t, and then we have kind of closed form formula for this kind of so this may look like completely coming from nowhere. But I'm going to talk about a bit heuristic of this kind of formula, I think, towards the end of talk. So at this point, actually, we have another one. which we can compute very easily. And then this is actually you have this closed form and then we can output these steps. So what is the feature of this algorithm? So this algorithm is going to compute on top of this gradient descent this estimate for this matrices, this tau and rho, which is of size t by 2. Okay, so compute these matrices. So this is a few computations on top of this gradient descent iterate. And once you do that, you get a consistent estimate of this unknown fraction matrices. And with this, you can basically construct the devised statistic in a complete data. So this is the final form. The final form is we just use the output of this gradient descent inference algorithm to plug in as in last case. And now everything is complete data driven. Okay, nothing is oracle, everything is complete data driven. And this device gradient descent iterate with the data driven devising coefficient is asymptotically normally distributed. So if you compare with what happens for this lawsuit, so you can see actually the structure similarity is very clear. Okay, so as I iterate, so you start with the estimate and do a one-step correction for its loss derivative. And then for gradient descent iterate, you start with the current iterate and then you do devising through a linear combination of all possibilities. Okay. So this is actually something also interesting. I think it's worth talking a little bit about. So from our theory, it's not only we can do inference for unknown signal, but also we can do something, for example, trying to estimate the unknown generalization error. So what does this mean? So the generalization error is really just the loss inferred on the unseen data given the current iterate. So for example, you already compute your iterate as t's iteration. I'm interested in what is the generalization associated with this t's iteration, and then I'm going to compute the loss under the near data. Okay, so this is something unknown because actually we don't know this kind of the unknown signal. And then the question is, can we actually estimate this generalization error just using our proposals along the iteration of and actually we can. And the idea is now we're going to use a device version, not for the gradient descent itself, but use a device version for this data matrix transpose, the data matrix applied to this gradient iterate. We use a device version for this statistics and then do a plugin estimate. Okay, and this one is going to give you a consistent estimate of intervention error. So again, the key point here is that we're going to give a completely data-driven estimate of the generation error without knowing the outputs. So now let me give you some simulation results. Yes.
So I have a question for the rates. So the rates for corrections where the same CD as this, and we have like a sense of like calculating correlations.
So this balance on is extreme balance because we don't have any assumptions on convexity. So typically you can just symbolize on your constant convexity, but if you want to work out this special balances roughly, I think it's roughly or this is not going to. I think the key point here is that we're actually working with the extremely non-convex case, and then the worst case dimensions on C is probably going to be exponential computation. Because you can see that algorithm can actually quickly blow in these non-convex evidence because use micros. So in a way we are kind of like working case that the algorithm we should not. So the point is that these kind of conditions does not rule out this blowing up and we should fix statistically. So the dependence on the C will be identified like that. And now if you work with a bit more stuff, we don't think but we have strongly convex problem. This one should be improvable. Other questions? Okay, so now let me give you some numerical illustration of what the algorithm is actually doing. So, for example, let's go back to this working example. We start with our plot, which is kind of a toy example. We have a one network. We have a signal, which is the signaling function, and then we have a slope. Okay, so in this example, we already see that the loss transcript is going to be quite non-convex. But then we're going to run our inference methods for this point. Okay, so this is not well trained. You can see these kind of things very consistent across layers of type of simulations. So, for example, we're looking at the estimate for the generation error. So this is the part of the estimate of the generation error. So the solid red line is going to be the unknown generation error associated with each iteration. Okay, so this is part that's unknown. And then our goal is trying to give a data-driven estimate of this generation error. And then what we can do with this is now using our proposal, this is actually it's roughly it's going to match exactly with degenerate error in these simulations. So what is the benefit of doing this kind of inference? So this kind of estimates is going to be accurate essentially along each iteration. And then you can see a very common phenomenon in this gradient and training is that looking at the degeneration error, it may not achieve the minimum at the end of training. So this is actually a very well-known phenomenon known as the early stop manipulation. So for example, in this example, you can see that actually the minimum point of the degeneration error is actually achieved just at a few iterations when we start the algorithm. So of course, analytically, we may or may not be able to categorize this point with closed form. But with inference methods at hand, we can numerically see where the product is going to be minimized. And actually, we looking at the minimization point of this estimate is almost going to basically it's going to match with this theoretical minimum point in this. Okay, it is of course one good part of you can have this kind of inference methods. The second part, we're looking at what happens for this confidence interval for the quantum sigma, and the picture is positive sigma. So we get basically a valid confidence intervals at each of those. So we just basically run this algorithm. As the estimation, we run algorithm for about 50 iterations. And we see that at each iteration, basically you get this valid confidence interval, this valid coverage at each iteration. And then we can also plot what happens, for example, to compare the length of the confidence intervals with the CL1. You can see actually the length of the confidence interval also has this pattern. It's going to decrease first, and then it's going to increase a little. Okay, but quite interesting what you see in this plot is that the minimizing point of the generation error, it does not have to be matched exactly with the quality of inference in terms of the length of the confidence interval. So this picture shows you that actually minimizing point of the confidence length can be in some way at the left of the minimizing point for the generation error, meaning that you basically first achieve the best quality of inference rather than generation. But the picture actually can be reversed for different choices of this kind of confidence. This is not inverse. Okay. But categorizing this kind of phenomenon, of course, is way beyond what we can do in a single paper. But still, these kind of inference methods can give you kind of a qualitative feeling of when you can actually stop the algorithm depending on what your goal is in terms of inference for doing.
So, this sort of plot, so if you have different initializations, how would it?
So this is just result. So in this one is for Gaussian initialization. So we have not tried the example spectrum by loss. Actually, I think if we do data-driven initialization spectrum, we can have the sense of being different. We're happy to assign different modifier because we start with something similarly dependent on the different. But if we start with an independent initialization, since we work something.
So the question, so with this integrations you can track like where you stop without having access to the also. Yeah. But do the measures the state evolution part for tracking, and that can also present like a hyperparameter like the realization spread.
In principle, you can also plot in terms of the regulating sense and then try to pick what is the best of the language and it's going to require more demanding computation because it's going to be each equation application for lots of regulating parameters. And actually, the optimum can vary differently across each of them.
So the state evolution of cell doesn't count.
The solution you have this factor formula, right? That's not how to put it. Then it's difficult to compute in very close points. For example, in a very simple case, in square loss bridge case, you can do some stuff in the matrix case, but in this much more complicated settings, typically you really cannot compute it in a very close form. Actually, I think I'm using some. The questions are now. Anyway, so let me just quickly go to the next one. So far we've been talking about things a bit more formal in terms of the one-layer neural network. Now, of course, everything is in principle. We have kind of captured the fundamental of the problem in terms of we have a very non-convex form. Okay, we have not any convergence guarantee, but still you can perform iteration by iteration inference. And all these kind of things actually are captured from data service in this multi-layer management already. So let me give you some quick notation. I probably won't spend too much time on this part because it's kind of conceptually similar. It's just the architecture are more complicated. So we're getting this multi-layer neural network. So what we do is you have an input feature, and then you're going to iterate. You're going to recursively compute with a weight matrix and then a function activation. Okay, this is basically what you is a picture of this non-linear network. So Q is going to be the network width. Typically, it's going to be the maximum width of these layers, and L is going to be the depth of this neural network. So we're going to run a green descent again on this object because we're going to be experiment in a way that we don't really understand. We are extremely vulnerable. We don't know too much about this kind of behavior in particular. And still, the goal now here is we want to do something interesting. So now our theory tells you that actually for this vanilla green descent, we can characterize the distribution of these weights, the dynamics of the weights. So for example, you're looking at the first weights with the problem of weight, and it's going to be in distribution, it's going to be a linear function applied to a bunch of Gaussian functions. So in this sense, the first layer is going to be approximate Gaussian. Okay, and for the second layer and the deeper layer, because the outcast we're going to consider is kind of finite width, so I don't want to talk too much about technical details, but this one will concentrate around the deterministic matrix. Okay, and then these kind of linear function delta, this matrix V and these Gaussian laws are computed recursively by what we call state evolution. I'll show you this kind of performance vector. So now let me directly go into this picture. It's kind of like a qualitatively similar thing that we have seen in the one neural network. But now we're dealing with a multi-layer, which is a much more complicated object than the one layer is. And we still see we can estimate this generation error quite well. This is what happens for 2 layers setting, and what happens for 3 layers, and then what happens for 5 layers. So what is interesting in these things, of course, I mean, you can try to cook up toy models for which you can capture some of the qualitative feature, but I think to work with in a bit more general settings, you can actually estimate this generation error just from the data, and you see actually there's some interesting phenomena. The first one, we're looking at what happens for this 2-layer setting. We can also see a trend of the first looking at a decreasing generation error, and then an increasing pattern. Okay, this is something very common actually in training. Another interesting point, and also quite common, is that you're looking at what happens for this one is a 5-layer neural network. So for this kind of neural network, we already have lots of parameters, and then we have to use a large step size to actually make the weights to move. And then during the initial phase of the training, you actually see that the error is going to go up because you use a step size, which is quite the error is going to go up. And then you're going to see a substantial decrease of the generating error because you first move the width a bit and then become a bit more effective, so the error is going to go down. And after a while, you see that actually the error is going to keep roughly the same. So the algorithm does not seem to perform substantially better from the iteration, let's say, 15 to iteration 17 in terms of generalization. And there's actually a very long line of work now in terms of this incremental learning of this neural network bringing some training. Basically, the key message there is that you have this kind of training dynamics for which you're going to remain in the same place for a long time. And then after a while, you will see a sudden drop of the generating pattern. So we don't thought that we actually, when we run this experiment, maybe about 200, it actually becomes a series of the conventional burden is going to be very huge at a given point. So we didn't basically put this sort of here. But basically, what the point here is that what we have is we have a proposal to estimate this unknown generation error, and we can capture these phenomena, actually not theorem, but in theory. Okay, so this is actually giving you as inference, or sometimes if you want to stop over here, then that's stop because you see the estimate is going to basically remain the same for this expression. Yes.
So there's a proposed approach can also capture the weights.
If you have unknown weights. Okay, so I'll be brief on this part because it's conceptually because I want to say something for talking about what is the theoretical underpinning of all this kind of new developments. So now let me briefly talk about the theoretical tool that we try to do for this kind of seeding. So we're going to develop a kind of a dynamic community theory, the so-called dynamic community theory, or the state region theory for a general class of first order algorithm. And this algorithm has a name called the general first order methods. So in the abstract formulation, these methods are being followed. So we start with an initialization. And then we're going to do a nonlinear transformation. And then with a nonlinear transformation, we're going to apply a matrix to get the next iteration. So with this next iteration, we again apply a nonlinear transformation. Okay, and then we apply a matrix multiplication again. So it's going to alternate between a matrix multiplication and a nonlinear transformation. So why is this kind of abstract formula is going to be helpful and relevant in our setting is now we can actually rewrite this gradient descent algorithm in terms of exactly the same structure. So let's just take this proximal gradient descent as an this is our proximal gradient descent algorithm. We just compute this. We have a closed form formula, and it's one linear upset. So we've computed everything up to t minus 1, and then we have a closed form formula update for the iteration t. So what is the structure of this iterate? We have computed the iterate as t minus 1. Okay, and then what we do, we're going to multiply by a matrix A. So this is going to be a matrix multiplication. And then once we multiply a matrix, we're going to apply a nonlinear function, essentially given by the loss rule. Okay, so it's going to be a nonlinear function. And with this computed, we again apply a matrix multiplication. Okay, so this part computed, and then we apply this proximal operator, which is going to be nonlinear function if you have a normalization. So you can see actually the general structure for this iterate is again in the form of an alternation between a matrix multiplication and a nonlinear function transformation. So this basically gives you the sense of why we want to start with this kind of an abstract formula just to calculate the central structure of the problem. So here's our theory. So our theory shows that actually these iterates we can characterize the distribution in a very precise sense. So suppose now we have a data matrix, which basically is assumes symmetric just for simplicity, independent mean 0 and 9 entries. And then we're looking at the joint distribution of your iterate. So the iterate is going to be a vector of high dimensions. So we're looking at the joint distribution of this iterates from iteration 0 to iteration t, and looking at this jth coordinate. And then the basic categorize, so this is going to be basically a length t plus 1 vector. So we can categorize the joint distribution of this vector in terms of a nonlinear function applies to a low dimension Gaussian. Okay, so these are Gaussian, basically the Gaussian variables, and we're going to apply a nonlinear function and get an explicit error bounds for that. So I'm not going to show you exactly how this formula is going to do for recurrence from this function theta to this Gaussian, but essentially you start with a trivial function, you start with like the map is going to identity, and then you compute this Gaussians depending on this functions f and g, and then you do this kind of things recursively. Okay, so you can determine the functions theta and the Gaussian laws these recursively in this formula. So I'm going to skip this technical comments on how these things are proven because it's probably not interesting to the general audience. So lastly, I think because I don't have that much time, I want to give you some heuristics of how we actually write out this goodness and inference algorithm. So just a quick recap of this content. So we confine ourselves in this one layer neural network and consider the proximal gradient descent algorithm. Okay, so this is our algorithm. And now we have a theory that characterizes essentially the distribution of the iterate itself and the iterate multiplied by the matrix A. So it takes the form that, for example, in this iterate is going to be a proximal operator of the linear combination of all past iterates, and coefficient is given by these matrices tau. And then we have a single component and a Gaussian box. So the goal of this gradient descent inference algorithm is we want to construct a data-driven estimate of these basically linear coefficients. Okay, this is the goal that we want to do. So how can this be done? So we give you the formula, but I haven't talked about how this actually can be done. So this is actually done in terms of the state evolution formula that we'll talk about in terms of our theory. So the state evolution theory tells us, if you just apply the state evolution theory, tells us that we can categorize the distribution in a bit more abstract way. So we can categorize, for example, let's look at the second one. The second one is probably easier to understand. So my claim is that the gradient iterate is going to be an abstract function applied to a bunch of Gaussians. Why is that going to be the case? It's because you're looking at this representation. Okay, so the representation tells you that it's going to be a nonlinear function applies to a linear combination of 4 past iterates plus some Gaussian. Okay, and an iterate is procedural. What you have is you're going to basically end up with a nonlinear function applied to the online Gaussians. Okay, so the actual formation should expect something like that. So the state evolution is going to give you a way to theoretically describe how this kind of function is going to determine through this chain. Okay, so the point here is that suppose everything is completed up to iteration t minus 1, we can compute these nonlinear functions, gamma t, which characterize the behavior of a mu t, and then compute the law of the online Gaussians, and then compute this matrix tau, again compute this function omega t, which characterizes this union of the previous iterate, and compute this matrix tau. So the formula is explicit, but it's not going to be typed because you can just write by hand what happens at iteration and say t equals to 100. That's impossible. And then our goal is actually not going to give an analytic function. We're going to give a data estimate for these measures. Okay, this is our goal. So conceptually, what happens is we have a formula that tells you essentially how you can actually go from iteration t minus 1 to iteration t with this kind of theoretical function. Actually, we don't know the closing formula. So we're going to kind of looking at this state evolution and getting a data estimate for this point is I will show this one is feasible. So now let me just focus on how things can be actually constructed. For example, going from iteration t minus 1, from row t minus 1 to top. Okay, just looking at one of these things to be. So in this construction, the matrix row t will go through a potentially complicated function, which we call gamma t, and then it will pass information from this function to this tau t. So how is this function determined? So this function is determined through the past matrix, the past everything is this function is going to determine through all past information up to iteration t minus 1. So technically, it's going to be determined by this matrix flow at t iteration 1 and all functions up to iteration t minus 1. So this is complete form, which is not too important. But actually, the point is that we have a closed form. So the dependence at an abstract level is going to depend on this matrix, all elements, and depend on this function up to iteration t minus 1. Now, once you computed this function, so this function is deterministic, nothing like okay. And then once you computed this function, you can evaluate this matrix tau t through the derivative of these functions. So what's going to be so this looks quite complicated, I understand. And what's going to be relevant and for purpose? So essentially, the goal here is we want to construct the Bayesian estimate of this matrix tau in terms of what you have for this matrix row, right? But now what we have is we have in some way in the middle we have this kind of like the undesirable functions that popping up. So essentially the idea is we want to construct a data version of this kind of derivatives. And why is it impossible? So because we have closed form formula for this function, we can just figure out recursions not only for the function itself, but also for this derivative. And the recursion for derivative, you're looking at this axis formation. So how is it dependence? The dependence of this derivative is actually going to depend on these quantities. Theoretically, it's going to depend on this matrix flow, and also depends on the bunch of functions which is coming from your derivative calculation. And these functions, if you're looking at this guy a bit more closely, you can actually see this is basically, you can think about this guy is going to be a function of these things. And then we want to estimate these derivatives. So basically, we want to estimate on these quantities. And then for row t minus, so we already have the original estimate. We basically this condition now we already have the estimate. So the remaining part is what is this complete looking in terms of popping here? And actually, this is where our theory is popping. So our theory gives you a calculations of these terms in terms of example, in terms of the iterate as t minus 1, and these terms are just what you observe for the data 1. So in principle, the story here is that we can construct the general estimates entirely in terms of observable data quantities, and that's the way we can close the loop of the construction. Okay, so I'm not going to. Yeah. Okay. Sorry.
Stop it.
Yeah.
Well, give us 1 minute.
Okay.